Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the interim director of NITheCS. And today I have the big pleasure of introducing to you Professor Stefan Lotz. Stefan is a professor at Northwestern University, but he also works with SANSA in the South African National Space Agency in Hermanos. Stefan studied, made his PhD at Rhodes University around 10 years ago. He's an NRF-rated researcher, and he's working. Sorry, and he has this affiliation as well with the Northwestern University, where he works on the master deep learning deep learning research unit. Yeah. He's an expert in space weather, yeah, but he's also very much interested in machine learning methods and the interpretability of complex models. Yeah, and another reason why I'm very happy that Stefan is with us this afternoon is that he's one of the PIs of one of the research programs of NITheCS. In particular, the one called Machine Learning in Theoretical and Computational Sciences. Yeah? And today he will speak about knowledge discovery in time series data. Stefan, we are very happy that you are with us. You already started sharing your screen. Okay, before I give you the green light, sorry, I always forget to encourage the audience to pose questions using the Q&A facility, yeah, which you find at the bottom of your screen. And maybe towards the end of the talk, when we start the final question round, you're welcome to raise your hand, and I can give you the right to speak in person. A few weeks ago, we had the request from some member of the audience to enable the live transcript facility in Zoom. So if you would like to see a live transcription of what is being said during the talk, just press on the live transcript button that you see at the bottom of your screen, and the transcription should appear immediately on your Zoom screen. Yeah. So Stefan, enough from me. People are here to listen to you. You're most than welcome to start your presentation. Thank you very much.
Thank you, Francisco. Yeah, so thanks for the good introduction. I think most things have been said. So I'm based in Hermanos and working for SANSA, so that's the National Space Agency, and we mostly look at space physics and space weather, solar physics, that kind of thing. But that's not the topic of this talk, although some of the applications or some of the examples I'll show will come from that field. So we might need to put our physics hats on every once in a while. Okay, so the title of this talk is Knowledge Discovery for Time Series in Deep Learning Models. So we'll cover a little bit about deep learning and where it fits into the broader concepts of machine learning and AI, just to set the scene really. And then we'll talk specifically about how deep learning is used for time series problems. We'll first define what we mean, at least in our case, what we mean with a time series problem or with a time series, and we'll give a little example from geophysics. And then we'll shift the focus a little bit to interpretability and explainability. Those terms are kind of used interchangeably. And then we'll talk about this NITheCS project, so where we're headed with the current project and then the timeline. So.
Stefan, sorry
Yes.
to interrupt. I just see a comment in the yes. chat that people can't hear you very clearly. Can you speak maybe a little bit louder?
I will speak louder. I'm just going to also try to set my. Sorry. I'm just going to try to set my microphone volume a bit higher as well.
Okay,
is that better?
Yeah, that's 100%. Thank you. Maybe the setting was a little bit on the soft side of things. Thank you very much.
Yes. The person who asked my cheese. Sorry about the pronunciation. Can you hear?
Yes, that's perfect now. Thank you.
Okay, good. Okay, sorry. So I just went through the outline of the talk. You can see it there. So we'll do some definitions, and then we'll end up talking about this project specifically, where we are, what we are aiming to do, and where we are headed. Okay, so the sort of classification of deep learning, I tried to use this notation just to identify where deep learning falls within AI, machine learning, and neural networks. So when we're talking about artificial intelligence, it just very broadly means we want to mimic human intelligence with a machine, right? So that comes down to a lot of, there's a lot of options, mostly or sort of classically heuristics and searching. So think a chase robot very quickly going through all the possible moves and then making the decision. A lot of it is probabilistic, for example, Bayesian networks, that kind of thing. That's what we're talking about in broad terms, what we mean with artificial intelligence. A subset of that then can be machine learning. So that means we don't have specific rules to write down. So we ask the machine to learn from data, to learn from experience, and usually that experience means just looking at large data sets, right? So there are very little or no specific hard-coded rules, although you can still do that to help the model. And examples of that is things like decision trees, k-nearest neighbors, and then neural networks falls again now within machine learning. And then what we mean with deep learning is basically just modern neural networks and the design and the methods and the algorithms that go along with that. The word deep comes from the fact that modern computation facilities can handle networks with very many neurons, very many layers. I am just going to mute my. I just want to mute my mailbox, otherwise it will be making noise. Sorry about that. Okay, sorry about the disruption there. Can everyone still hear me fine?
Yes, we can. Thank you.
Good. Sorry about that. Okay, so what we mean with deep is just many nodes, and many nodes have been is something that was enabled by mostly hardware, and then the algorithms that go with it. So utilizing GPUs, smarter ways of training, smarter ways of segmenting and annotating data. All of this together enables what we call deep learning today. And examples of that are the usual MLP, so that's a multi-layer perceptron. That's the normal basic picture we have of a neural network. But these days there are so many shapes and topologies and things going around. So from convolutional networks that are used a lot in image processing to TCN, so that's temporal convolutional networks. That's sort of the modern version of the old recurrent networks, ALMA networks, that kind of thing. So that's more specifically catered for time series problems. So modern deep learning is very wide. The field moves very quickly, but it's for our purposes, we just need to understand that it means modern neural networks, right? Okay, so this is a slide I used recently for a sort of public outreach talk, but I think it's useful. So what is a neural network? So imagine you have this. You're the sound engineer taking over from the previous guy that left without leaving any notes, right? So you have the final mix of the recording. We have that. We have the inputs. We have the instruments and the musicians ready to make the music, but we don't know what the mixing desk did to arrive at that final recording. So a neural network is basically the task of reverse engineering this final mix. So I know this is a very basic example, but it's useful to just visualize this in a sense that we have access to the inputs, at least the ones we think that went into the mix. This set on the left-hand side here may definitely be incomplete, and we know what the output looks like when we're talking about supervised learning. So we know what we are aiming for, we know what the inputs are, but we don't know how to get there. So that's just in very broad terms what a neural network is and what the training then involves. A little bit more more formally. So what I wrote down here is a very small, very basic two hidden node, one hidden layer network. So we have two inputs, so we can think about that as our musicians. We have a guitar and a drum, for example. We have two hidden nodes, so there's two knobs on our mixing desk, and we have one output, a single track, right? What's important to note here is that, at least for this case, these are fully connected, so there's a connection going from every node in the current layer to every node in the next layer, and these are weighted by these weights. Every node has a activation function. We keep these at least the same per layer, usually, at least. So in this case, the hidden and the output nodes has this ReLU, what we call a ReLU layer. So it's a sort of a linear function that's zero for negative values, for negative input values, and on the input side we have just a linear activation function. The point to get here is that the activation functions can change. The nodes are all connected by weights, and to go from the one layer to the next layer, you just add up. So to go from the green layer here, the input layer, to the blue layer, the hidden layer, you just add up the input nodes, multiply by the weights, add a bias, apply the activation function G, and you get your output at that node. You repeat the process, rinse and repeat recursively until you have your output. So that's what I tried to write down at the bottom layer. So at every layer K, so for a network of K layers, if we expand the thing a little bit now, so now we have many hidden layers. So for a network of K layers, we have this recursive weighted sum that goes into that goes layer by layer, and in the end you have your output layer, right? So the secret sauce here is, this doesn't look very complex when you just write it down like this, but now imagine there's not a few nodes, but thousands or tens of thousands or even millions, and that these activation functions are always nonlinear. So the nonlinearity of this function G enables or creates the nonlinearity of the neural network. Otherwise, it's just linear regression. And you can increase this by increasing the depth. You could increase the complexity of the model. And I'll combine that with all the modern training techniques, and there you go. Now you can, drive a car or make a Netflix suggestion. So this is kind of a slide, a note for myself, really. I was trying to think, how do you just in a single sentence or two, how do you write down what you mean just in mathematical terms? So so we assume we have this model, this neural network that we call F, so some unknown function F. And we are trying to estimate this output parameter y by learning from the inputs x, right? So we learn from the input x, and y. How do we learn from x? We solve this optimization problem, right? So we approximate y using x by setting these weights to somehow arrive at a small error, whatever small means in our case. So in the usual case of when you train a neural network is you solve this optimization problem, which in words just means find the weights that reduces the error below some threshold. I called it epsilon 0 there on the testing set. So we have some data set that we keep aside. We test the network on that. And once we arrive at some small error, now we're saying we have a model, which will still have, obviously always have a error, but now at some stage we'll be satisfied that this thing is working, right? So if we think back to the previous slide, so what does this mean? We just recursively projecting our input x onto some function space. So if we think about the set of activation functions as a set of basis functions, and we kind of recursively project and project and project back onto this space G, I guess then we arrive at something that looks like this top equation here. Like I said, this is more of a speculative slide than anything concrete. That's just the way I'm thinking about this problem. I'm not sure if I'm correct, and if anyone has a better idea, please share it. Anyway, so we said we wanted to solve time series problems, but now what do we mean with a time series? Again, so we have some output parameter that we want to predict. Let's call it y. It's measured at some point at some time t. And
Sorry, Stefan.
yes.
Your mic again went down.
Oh, that's very weird. Sorry. Oh. That is very strange. I can see it going down. Okay, is that better again?
Yeah.
Yeah, thanks.
Sorry about that. I don't know why this happens. Okay, so we have a output at time t. It's driven by some function, or it's the relation between the inputs x and the output y is some unknown function f, or no, some function f, which is a function of x and t, right? So we have the outputs at a number of times. We have a number of inputs, so that big X is just the set of input parameters, x1, x2, up to xk. We assume there's k of them. And you notice here that I write tau1, tau2, and not t, right? The point that we want, the kind of problem we want to solve here is that this time dependence of the input is not simple, or is not trivial.
Sorry, Stefan, again. Your mic went down again. Sorry.
I'm not sure what the problem is. It should be better now, right?
Yeah.
Yeah, now it's better. Thank you.
Okay, I really don't know why it changes automatically. Okay, please just say if it happens again. I will have to solve this as an ongoing problem. Okay, so the point here is that the relation between the inputs and the output with time is not simple. So we want a when we're talking about a time series problem, we're talking definitely about something that has time dependence, non-trivial time dependence. So it can be something like a constant lag, or in the simplest case, just identity. So just as usual. So the output at time t is dependent on the input at time t, or something that correlates with the inputs. And I'll show an example of that soon. So this is what we mean with a time series problem, and then some of the assumptions implicitly and explicitly that we're making is listed here in the green block. So we assume causality at least. So the future values can't determine past values. We do assume interdependence between, so if we measure some kind of information between the input parameters, we assume that they are related somehow. However, these interdependencies are not stationary, so they can change over time, or say with phase of the system, or with the condition of the system. And these delay functions are unknown and also not necessarily constant. And there can be some temporal feedback, so that the input parameter is somehow dependent on the output parameter at some past time. So these are the kind of assumptions we are making. I think this example will maybe give a bit more clarity on what I mean here. So like I said, I'm working at the space agency, so some of the stuff we look at has to do with the Earth's magnetic field. So this weird shape that you see here. So the Earth's dipole field is always distorted by the outflow of plasma from the sun. So the problem we are looking at here is something very simple, at least if we work with this estimate. What is the distance between the Earth's surface and the outer edge of the geomagnetic field, or the magnetosphere as we call it? So what is this distance as a function of the pressure in the solar wind? So there's a plasma emitted from the sun. It has magnetic and just normal dynamic flow pressure. And these two plasmas push against each other. So the plasma within the magnetosphere and the plasma in the solar wind push against each other, and this leading edge of the Earth's magnetic field is being pushed towards the Earth as pressure increases, and then expands as pressure decreases. So on the right-hand side here, you see this fairly simple equation. So this is just an estimate. So the magnetopause standoff distance, this RMP at time t, is dependent on some function of the pressure. So the pressure here is just the velocity squared times the density, right? And to this square root of the pressure. But yeah, so like I said, the magnetosphere size is determined by the solar wind pressure. It varies with this pressure. The problem is that this time dependence is dynamic and depends on the speed of the solar wind. The reason for that is when we measure this incoming solar wind, the satellite sits out here in space somewhere. And as it measures the plasma going by, the time for that plasma to propagate from the satellite location to where it first interacts with the Earth's magnetic field is dependent on the speed of the plasma, right? So now we immediately have this non-constant tau that I talked about in the previous slide. So in this case, this time shift is dependent on the distance and the speed. So the distance to the satellite and the speed of the solar wind. So this is a very sort of basic, it's not really even a problem for space physics, but this is a basic setup of where we would find this kind of time series problem with a delay that's not constant. Okay, so that's the time series problem. So now we have a neural network. We want to solve it. We have loads of data. That's great. We know it's a little bit complex. We know the sort of time dependencies are complex and all that. So all those those time series problem assumptions are ticked. And now we get to interpretability. So assuming we have a model that can solve this problem.
Stefan, your sound went down again.
Okay, I think I know what happens. It is
okay, now
somehow clicked onto my mouse scroll wheel. So whenever I scroll,
okay.
Changing the volume. I think I figured it out. Okay, so say we have a model that can solve this problem, but
I think you scrolled again.
word. Can't I just lock it? I'm not going to use the mouse. Okay. Okay, so say we have a problem, a model that can solve this problem. Now we want to interpret whatever that may mean. So if we mean by interpretability that we want to figure out what the time delay is, say we didn't know how this system works, want to figure out what the time delay is, say we wanted to know which solar wind parameters is causing the magnetosphere to expand and contract, if we didn't have this estimate, now we need to look beyond this black box model. So what do we mean with interpretability? So we want to go from this top part of the picture to the bottom part, the today part to the XAI, explainable AI part, where we go from a situation where we do not know why the model predicted what it predicted. We do not know when it's going to fail or when it can be trusted. And the user really is a little bit in the dark here. And we want to go to a situation where we understand why certain predictions were made, why certain decisions are made. And as a sort of an outflow of that is how do the input parameters determine the output exactly. So there's a bunch of, there's different ways to look at this. So of course, the first prize is that the model is so simple, you just look at the data and you understand what's going on, right? So that's first prize, and not a lot of effort needed to go into that. Secondly, there's sort of the global explanation where we talk about directly interpretable models. So that's something where we can write down an equation like that, and we more or less can understand what's going on just by looking at the equation. From there we can look, so we sort of zooming out into obscurity. We can look at local solutions. So that means you evaluate certain individual predictions to guide the understanding. So imagine building a self-driving car, and now you want to see how it reacts to a horse or a bicycle or a truck, whatever. Then there are these sort of post hoc interpretability techniques where you have your black box model and you apply it globally to the model to gain some kind of insight of what was done. So you don't need to know you don't need to be really involved in the creation of the model. The interpretation happens after the fact. And then again, post hoc, again, you run various samples through the model. Again, it's sort of a black box, but by running specific and sometimes sort of adversarial examples, you can gain some kind of understanding. I'm just going to go through a few of these options. So when we talk about directly interpretable, something that's really been coming up a lot recently is this idea of symbolic regression. So you start with this sort of a library of simple equations, and this is really, some of it really fundamentally makes sense because nature seems to work with fairly simple building blocks and building expansive and complex things out of that. So you start with this library of simple equations and your input and output data set, and then usually by by some kind of brute force combinatorics, you iteratively build up the equation that will solve your problem. The picture there on the right hand side shows it pretty clearly. And there's a few recent examples of some really cool things that's been done. So there was a derivation of Newton's law of gravitation from planetary trajectory. So this model skipped Kepler completely and just the equation that popped out in the end was something that looked like the gravitation law. This fourth example there, the Feynman project, they just took the first, I don't know if it was the first 100 equations or a select 100 equations from the Feynman lectures, and they could solve all of them more or less as they are written down in a textbook, better than whatever the state of the art was at the time. This is something built by Max Tegmark. Okay, so this is something that we need to take note of, but it's not really specifically a deep learning solution. These methods use fairly simple neural networks as parts of the building blocks, or to subdivide the problem, but not really as its basis. More directly related to what we're going to do is where you design a network for interpretation. So this what we called pairwise nets. I did this with a master's student a couple of years ago. So we just built this fairly simple looking network. It's the one at the bottom left there. Fairly simple looking network that enables these pairwise interactions to be handled separately, and you have this these summary nodes, and those summary nodes provided some kind of guide as to the importance of each pair of input parameters. The nice thing about this thing was that it was more or less dynamic. So on the example on the right hand side there, we could identify which solar wind parameters are so in the task of predicting a geomagnetic storm, we could see which of the solar wind parameters were important at which phase of the storm. So usually this situation is fairly dynamic in the sense that at the start of the storm, it's more the pressure in the solar wind plasma that causes the problems, and later on it's the magnetic field in that plasma sort of becomes the more dominant term in terms of what the reaction on the ground will be. And we could see this happen. So in this case, the cons of this method is just that it's computationally quite expensive and not something that you really want to use on an unknown problem. We knew how this problem worked already, so we could test this network. But the point of these interpretable, directly interpretable models, in this case at least, is you design the network, design the layout of the network so that it is easily interpretable. And there are other ways to do that. This GummyNet use general additive models. Very similar idea, and it works, but it's computationally expensive. And now when we move to this sort of postdoc ideas, this goes a bit closer to sort of information theory and looking at information flows. So SHAP or Shapley values based interpretations just uses this idea from game theory, where the payout or the information is or the contributions is divided between the input parameters. So in the end, you get a share of importance between the inputs, and this can be used as interpretation. So if by interpretation we mean which input is important at which time, then this is the one way to do it, and this is sort of more or less model agnostic. So you can use it on any type of network. You don't have to design something to be interpretable in that sense. Another option is this sort of backwards propagation. So it's relevance propagation that starts at the output of the network and then propagates the relevance, or let's say information content, something like that, from the output through all the layers back to the input. And this is really useful to look at it layer by layer to see what the network does at every layer. So a practical example here is to assign a relevance score to pixels in an image. So if we want to know which digit was written down, we can now see which pixels are important for every digit. So this is a very trivial example, because obviously black on white on black, we know the pixels that make the 9 is most important to decide whether it's a 9 or not, right? But the point here is that this relevance propagation can be very useful in sort of a fine-grained way of deciding which input parameters contributes to every sample. And then another example of something we did also a couple of years ago. So we used something called temporal convolutional networks. So the convolutional networks are usually something used for images, but there's a way to sort of wrangle them to be useful for time series data. So in this case, every input parameter gets sort of copied and shifted back in time, so that we look back in history of every input parameter, and in that sense you have multiple time series of your inputs going into the model, and that's very useful for something that's for the kind of problem that sort of a build-up and triggering effect. So in this example, we used it to use these TCNs to predict solar flare eruption. So the task was to assign probability of eruption of every active area. So you can see the spots there on the sun, and each one of them gets a percentage. And in that figure on the right-hand side, we could trace various attribution methods. The Shapley one worked very well in this case. We could trace the value of those attribution values for each input parameter and see in the 24 hours preceding the flare which one of those inputs had their attribution peak, starting to peak. So we looked at those curves within the red shaded regions, and we could see some of the inputs starting to peak in the 24 hours before the flare. So this is a nice example where it did work. So I think about 28 hours after this prediction, that big spike there indicated that that specific active area did produce a flare. So that brown area in the figure produced the big X-ray spike that you see there. Yeah, so in this case, we used Shapley on TCNs, and it seemed to work. So the current work that we're doing for this project, sort of two things we're busy with at the moment, apart from just the toolkit development. So we want to create a test bed. So we want to make custom functions that look like the block function up there. So if we have fine control over how these interactions work, exactly what those time dependencies look like, and then select the basis functions, we can really design something of a given complexity and test our methods on that. So that's something we sort of a tool development for the tool. What we're also looking at again is this sort of geomagnetic space weather kind of problem, where we want to use solar wind data as input to a model that would predict what the effect on the ground is going to be. So predict some disturbance index on the ground. And the cartoon picture there just shows the layout of the situation. So you have the sun, the solar wind flowing out continuously, and then sometimes you have these massive eruptions, and those massive eruptions, which we call coronal mass ejections, then impact the Earth's magnetic field. After it passes our satellite, you can see my very pretty satellite design there with its orbit. These satellites orbit the L1, the first Lagrangian point, which just means it orbits empty space in between the sun and the Earth, and it always stays upstream of the Earth. So we have these inputs, time lagged, obviously, and then we have some kind of reaction that we measure on the ground. So what we want to do in this case, and this is a project that kind of runs parallel to this NITheCS time series project, but it will provide some valuable input. Our aim is to build two models, one at high latitude and one at lower latitude. So Hermanus is our low latitude station, Abisko in Sweden is our high latitude station, and we know that just the physical processes involved at middle and at high latitudes are very different. So we want to build two models, one for Abisko, one for Hermanus, and then look at the feature attributions and see if we can, using methods like SHAP, for example, if we can attribute the correct physical parameters to the difference we see in the reaction at these two places. That's just a time series of what it looks like, and just note the bottom two curves there. The point is just the reaction at Abisko is very different to the reaction at Hermanus. That's just a trace for a specific geomagnetic storm with the inputs labeled in red and the two outputs at Hermanus and Abisko in blue. Okay, so this project that we started this year, we had a kickoff workshop in March 22, where we kind of introduced the ideas and got some people together. Currently, we are working on the tool development, and we're using this DARTS framework. So DARTS is a time series module for Python that works really well with the existing deep learning modules like PyTorch. So we are busy working off of DARTS and then developing tools to utilize things like SHAP on TCNs. That's sort of the first task. Once we have that toolkit set up, we evaluate it on a synthetic problem, like I explained. Second step, evaluate it on a real but a known problem, so at least something that we can understand what we should see, and then we explore some additional applications. We have our own, what do we call it, mini workshop, or a specific day set out for us at the SACER workshop. So SACER is the South African, Center for AI Research, I think. So yeah, SACER is the sort of annual AI research workshop in South Africa, and it's hosted in December in Stellenbosch. So we'll be there for at least one day, showing what we came up with. Yeah, and in the future we want to utilize this to look at unsolved problems, and I think the application to time series is something that's sort of neglected a lot in the deep learning community. A lot of the focus is on I guess more difficult problems like image-based problems and self-driving, that kind of thing. Yeah, so we really want to find a few unsolved problems and look at it using this toolbox, and then obviously just explore next thing. What do we want this feedback to look like? I just put in this slide right at the end. We assuming the output of this thing would look something like a spectrogram, where we can see that with time, certain input parameters increase and decrease in importance. So this is just a SketchUp. Yeah, so we are assuming that once we have a solution, once we have a model that works as an extra output, if we can have something like this, which basically plots a spectrogram that would show the mutual information between the inputs and the output and how they vary with time, that would be useful. Okay, so that's it. I think I went a little bit over my time. Yeah, sorry for all the audio glitches. If there's any questions.
Yeah, thank you very much, Stefan. I didn't go over time at all. Thank you very much.
Okay,
That's
great.
absolutely perfect. I really enjoyed your talk.